Hi everyone. Welcome to the course Econ 7310. The course title is Elements of Econometrics, and my name is Dong-hyuk Kim, and I am the instructor for this course for this semester. This course is offered every semester. I am teaching in the first semester only, and someone else, Dr. Fu Oh-young, is teaching in the second semester. But the material is going to be the same. So I am the course coordinator, and I am a lecturer to teach. And my office is located in Colin Clark building. The building number is 39. And my office number is 538. Here, I have my email address. So if you have any question or anything to discuss, you can send me an email. Then I will try to get back to you as soon as possible, but don't assume that I can be fast during the weekends or after working hours, something like that. So, but anyway, I will try to answer to your questions as soon as possible. As you know, lectures are scheduled on every Wednesday. Time is 10 to 11:50. So this is basically a 2-hour credit course, and the location is right over here, building 63 and room 348. This semester I have 350 students, so I don't think everybody is here, but this classroom is pretty full. Last year I had 200 students, and the year before I had 100 students. So every year I have 100 more students. It's funny, but maybe that's why I have this semester I have 9 tutors. So although this class is really large, you're gonna have tutorial sessions. Each tutorial may have about 20 students, and tutors is going to lead the tutorial sessions. During the tutorial session, you're going to have a chance to run the methodology that you learn in this course using the real data. So during the tutorial session, you're going to learn how to use statistics or econometric software to analyze real economic data. So you need to sign up to a tutorial group using MySciNet. So if you haven't done yet, so please do so. You have to sign up the tutorial session. There are many tutorial sessions, maybe 18, something like that. So you will need to choose the one that fits to your current timetable. My consultation hours are scheduled on every Wednesday, 12:30 to 2:30. So I'm going to open my office door so that everybody comes in, and we can chat about the material, of the course material, or your life, things like that. So I'm going to try to make myself available to you guys at least as a minimum during my consultation hours, which is 12:30 to 2:30 every Wednesday. So right after this course. However, if you cannot make my consultation hours, you are very welcome to email me to set up another time so that we can meet and discuss about your problems. Okay? During the lectures, I'm going to cover theoretical methods mostly, and I'm going to give you some examples to help you understand. But the main thing is the theory, not the examples. Examples, you are going to again, you're going to have a chance to look through many examples during the tutorial sessions with your tutors. So during my lectures, I'm going to present a methodology, econometric methodology. Okay. Required textbook. In this semester, we are going to introduce new textbook written by Stock and Watson. The title is Introduction of Econometrics, and that this this textbook is widely used as an introductory econometrics text all over the world. So this is the textbook. Actually, this is an audition for instructor. Maybe you might have different cover design for student version, but anyway, this is the textbook. So this book is required for this semester. This is a really modern textbook, and we are going to cover more than half of this textbook. And all the exercises are coming from this textbook, so you better have this one. Recommended resource is Woodridge textbook. This one is equally good, but we choose to use Stock and Watson. I'm going to give you lecture notes, slides, and data sets and problem sets. So I'm going to provide other course material, excluding this textbook. I cannot buy the textbook for all of you guys, but I can write lecture notes and slides, things like that for you. So I'm going to do my job. And before coming to lecture, it will be better for you to preview the textbook, but that's not required. However, after the lecture is over, I want you to read through the textbook. That is very important. Okay? So this is learning activities for this semester. Today, I'm going to introduce this course, and we're going to talk about some basic example to motivate the course. And then we will review probability and statistics. Econometrics is based on probability theory and statistic theory. So it is necessary to have some background in probability and statistics. From next week, we're going to start talking about regression analysis. In the beginning, we will talk about regression analysis with one variable, which is the simplest case. And then after covering the one variable case, we're going to extend our model to have situations where we have more than one variables. So we will talk about multiple regressors. And then after finishing the multiple linear regression analysis, we will extend our analysis toward different data sets like panel data and the binary dependent variable, and we're going to cover a little bit more advanced topics like instrumental variable analysis and time series. Because this course is just introduction of econometrics, we cannot go deep theoretically. So I'm going to talk about theory, but I cannot provide all the proofs, things like that. I'm going to give you some assumptions, and I'm going to explain the results. And then we're going to talk about how to apply our methodology when you have real data. Okay, so assessment. Assessment is very important for you guys. So we're going to have two exams. One is mid-semester exam, and the first one over here, and the other one is the final exam. Mid-semester exam takes 20% of entire semester, and the final exam is 50%. Both exams are controlled by the university, which means I don't know exactly when those exams are going to be. So the university will choose a date for midterm exam and final exam, and they are going to monitor the exam. One thing I know is the midterm exam is going to be on a Saturday, either 30th of March, 6th of April, or 13th of April. But we don't know when exactly the exam will be. So when the date is chosen, I'm going to let you know of the date. We will have two research projects, each with 15% of weight. Here, I wrote down the due date, 26th of March by 5 p.m. And the second one, due date is 28th of May, which is literally the very last week. The due time is the same, 5 p.m. When you are doing your research projects, it's okay to work in group. So you can discuss with your colleagues, your friends, and you can solve those problems together. You know, I really encourage this because I believe that working together is useful. It's helpful for you to learn more. You can teach other people. By doing so, you can learn more. And you can also learn from your friends. However, when you write up your homework, you have to answer in your own language. Okay? So those answers have to be yours, not someone else. So after understanding the material, you write down your answers in your own language, which doesn't mean that it's okay to write things in Chinese or Vietnamese. You know, you have to show that you understand the material, okay? I'm not going to accept hard copy of your homework. You know, every homework has to be submitted through the electronic channel. So you have to prepare electronic copy, and you need to submit your homework through Blackboard. There will be a penalty for late submission. If you basically, roughly speaking, the penalty is like this. If you're late by 1 day, I'm going to take 20% off out of your research project. If you're late by 2 days, then I'm going to take 20 additional percent. So you're going to lose 40%. In this way, you're going to lose some, some points. Okay. So for detailed, you need to look at the course web page. I explained about the penalty in detail over there. But the rule is very simple. If you're late by 1 day, you will lose 20%. Every day, you will lose 20%. There's one exception. You know, if you have some medical reason or things like that, family disaster, then I'm going to accept late submission without having any penalty. But in that case, you need to provide evidence, documents. Okay. Okay. So I discussed about this already, and yeah, exams are not open book. So you are not allowed to bring textbook and lecture note, things like that. So you just bring your pen. Ideally, it has to be it. But you are allowed to bring your calculator and English dictionary, but those things have to be approved by the university. Some calculators are approved by the university, but not all. So you need to check whether your calculator is approved by the university before the exam. Last year, some students were very angry because they didn't check whether their calculators are allowed during the exam time. I hope nobody is angry for the same reason in this semester. To help you to prepare the exam, I will give you exams from the previous years. I think the final exams are all available through the library webpage. So you can download the previous final exam from the library webpage. But midterm exams are not available. But I'm going to give you last year's midterm exam. Okay, so any questions so far? Yeah, question. You are talking about the research project, right? Assignment. If you submit another one, then the previous one will be, disappear. Yeah. But your very last one has to be submitted before the due time. Yeah. Any other question? Yeah, with the school. There's a list of calculators. You can search for university webpage. Yeah, question? Sorry? How many? Ah, that depends. Yeah, that depends every semester. Yeah, I will have a better idea, few weeks later. But for now, I don't have idea. Yeah. Any other question? Okay, so this is basically introduction of the course, and we are going to start the material, the course material, by giving you a brief overview of the course. So, economics. Economics has lots of theory, right? And we study lots of theories from microeconomics or macroeconomics. Those economic theories are talking about the relationship between economic variables, say X and Y. So what economic theory is doing is, the economic theory can say something like this. When we increase X, then Y will decrease or Y will increase. So economic theory mostly say something about the direction of the Y variable when you change X variable. But economic theory doesn't say how much or the quantity of the change in the left-hand, the Y variable. So economic theory never suggests quantitative magnitudes of causal effects. We can talk about quantitative effect only when we have real data. And when we have data, by analyzing the data, we can say something like, when we change our policy, outcome variable will change this much, 3%. Like, when you have 1 year of education, then you're going to increase 10% of your income, something like that. But economic theory doesn't say whether it is going to be 10% or 20%. But it only says it will increase. If you study more, you're going to earn more money on average. So in order to say the quantity or the magnitude of the effect, we are studying econometrics. So here I list some examples. So what is the quantitative effect of reducing class size on student achievement? So here we have really large class. If we reduce the class size into half, then what would be expected student achievement? And the second example is if you do this master program, then compared to the situation where you didn't do master, how much earning you can make additionally. And we all know that when price increases, the demand will decrease. So if the government increases the price of the cigarettes, then people may smoke less. So the demand of cigarette will decrease. We all know that this is what economic theory says. But we don't know exactly what's the number for the price elasticity of cigarette demand. So by analyzing economic data, we can measure the exact number for the price elasticity of the demand. So using data, we want to do this kind of things. And in order to do that, we want to learn statistical method. That is what we are doing in this course. So let's think about an ideal situation. If this is not, if what we want to know is not related to human behavior, then we can run some experiments like other natural scientists are doing. So, for example, we develop new medicine for cancer, and then we want, so because we developed a new medicine, we want to see what's the effect of this new medicine. One thing that we can do is we buy lots of rats or animals, And then we group these animals into two groups. One is a control group and the other one is treatment group. And we give cancer. So we can initiate cancers for all those groups. And then for the treatment group, we can give medication. So everything is the same between these two groups, other than one group has medication and the other one didn't have medication. A few months later, we can measure the size of cancer cells, things like that. So any difference between these two groups can be interpreted as the effect of the medication. But in economics, we are analyzing human behavior. So many cases, experiments are not possible. So think about this class size effect. We choose school districts for high school kids, for high school education. So in this area of Brisbane, we have many school catchments. So we choose randomly school districts and then divide those districts into two groups. One is control group and the other one is treatment group. And for those treatment group, we reduce the class size by one student. If there's no movement between this school catchment, then this is an experiment, just like natural scientists are doing. But when we make educational environment for this group better than the other, then parents are going to think that, oh, that catchment has a better educational environment, so we need to move to that area. So people are moving to this new educational environment. So then, a few years later, even if we see the difference, we cannot say that this difference is because of the smaller size of the class. So when we are dealing with human behavior, almost always it's not possible that we can do experiment. So, unlike many statistics, econometrics has to deal with observational data instead of experimental data. We observe the market, and then what we observe is the result of human behavior. So from those observed human behavior, we want to identify effect of X variable, effect of Paulus change, something like that. Okay, so this is a very challenging task because many things are mixed together. So there are confounding effects, and the data doesn't explain everything because in principle we cannot observe everything about each individual. There are so many omitted factors, and also the economic behaviors are many cases. Economic behaviors are result from equilibrium behavior. So there's a simultaneous causality problem. And you have to really understand that correlation is not exactly the same as causality. So let me give you just a similar example again. When you graduate college, we all know that maybe your expected earning will be higher than those people who just finished high school, right? So this is what economic theory says. But we really don't know how much is the wage difference for those people who graduated university. So we can take a group of people, one group who graduated the university, and the other who didn't go to the college. Right? And then we take the average of annual income for this group and we do the same for the other. And then there must be some difference. Can we interpret this difference as effect of university education? If those two groups have the same population, then yes. Distributionally, college graduates are the same population as the high school graduate. Then, all the difference, wage difference, can be interpreted as the effect of college education. However, one thing that you have to really think about is maybe you might think that smarter people are more likely to go to university, right? If this is the case, then the wage difference can be because of the university effect and also because these people are smarter, right? So we want to separate out the effect of university education from the effect of smartness, all right? So we need to separate out, we need to identify the effect of education on the future income or employment rate, things like that, separating out all other factors. All right. So in this course, we're going to learn econometrics methods for estimating causal effects using observational data instead of experimental data. And econometrics, almost always, our objective is to identify causal effect. But sometimes, using statistical method, we want to do something else, like forecasting using time series. At the end of this course, we're going to talk about forecasting problem. But mostly, this course is about causality. But this course will introduce time series so that you can learn more advanced time series methodology in the next semester. And although during the lecture we're going to learn theories, I'm not going to go deep. We are not going to provide any proof or anything very serious. We just present the assumptions and the results, and we're going to talk about how to use this methodology when you have real data. And also, we're going to learn how to evaluate the regression analysis done by other people, which means you're going to be able to read some applied econometrics paper, academic paper. And also, I'm going to give you lots of examples for your tutorial sessions so that you can really use your computer program to analyze the data. Okay, so let me start with an example. This is an example of California test score data set. And the problem is we want to know the relationship between class size and educational outcome. Educational outcome can be measured by many different ways. But one obvious thing is if there is a national-wide standardized exam, then we can measure the educational outcome by the national exam. So we're going to do that. Policy question is, what is the effect of test score when we reduce class size by one student per class? This data came from California school district. So observation is, each observation, the observation unit is a school district. And in California, there must be a very large number of school districts, but we're going to use only 420 school districts. So the sample size is 420. We observe year 5 students, so 5th grade test scores. And the test score is a district average. That is not individual outcome. That is, we collect all the test scores and then we take average for each district. That is our the variable that we are interested in. And the policy variable is the student-teacher ratio. Sometimes I'm saying STR. Whenever we are talking about this example, I could say STR instead of school-teacher ratio. Then you should understand what I'm talking about. So let's look into the data set. So here, whenever you have data, first thing that you should do is you need to take the average. So what's the central, the representative number for the variable? The first one is school-teacher ratio. This is one of the variables that we have. And the second one is test score. This is the variable that actually we are interested in. For each one of them, we have average. So on average in California, the class size is roughly 20 students. And standard deviation is 1.9. So relative to the average, standard deviation is very small. So the variation seems to be small in class size. Test score, average test score is 650 roughly, and the standard deviation is about 20. And we want to have better idea about the distribution of those variables. So we have a percentile. So you should know how to read these percentiles. For example, 10% means 10% of districts has less than 17.3. So 10% of school districts has class size less than 17.3. Similarly, how to read this number is 25% of school districts has average test score smaller than 640. So this way, we can have some rough idea about the distribution for each variable. But this is just the beginning of the analysis. We just summarize the distribution, but this table itself doesn't say anything about like the relationship between test score and student-teacher ratio. It doesn't say what would be expected outcome on test score when we reduce the class size. So we need to go further. We need to look into the data further. So another thing that summarizes the distribution, especially when you have two variables, is we can construct scatter plot like this. Then we have better idea about the relationship between those two variables. However, unfortunately, these scatter plots are very widely scattered everywhere, and it's hard to know whether looks like there's some negative relationship, but we're not sure. Still, this is like eyeball testing. This is a visual representation, graphical representation, but by looking at this graph, we cannot say that when you have reduced the class size, definitely you're going to have better student outcome. We cannot say something like that. But this is a useful thing to do, to learn, to have picture of the distribution. So, so what we want to have is a numeric evidence on whether districts with low STR have a higher test scores. So basically, we want to measure something. We want to estimate, and then after estimating the outcome variable, we want to run some hypothesis testing, and we want to summarize the uncertainty around our measure using confidence interval, things like that. Okay. So from now on, what we are doing is we categorize our data into two groups. One is a small class size, and the other one is a large class size. And then we measure the difference in terms of test score between these two groups. And then after estimating the difference in test score, we're going to test our hypothesis that there is no difference. And then we're going to construct confidence interval. We are going to do these three things in the beginning of the course. That is because we're going to keep doing this over and over again, using different data set, using different econometric method. Basically, what we are going to do is we're going to estimate something, and then we run hypothesis test, and then we're going to summarize our uncertainty around our estimate using confidence interval. So although this is a really simple exercise, but this is going to be base for everything else we're going to do in this semester. Okay, so I want you to understand, I want you to follow this example. Sorry. Okay, so we partition our sample into two groups. One is a small group, and the other one is a large group. So when str is less than 20, we define that those districts are small class. Otherwise, those districts have large class. And then for each one of them, we take the average score. So here we have numbers. For small group, we have average score of 657, and for large, we have 650. And we computed the standard deviation because this is a random variable. There's a variation within each group too. And we have sample size for each group. Initially, we had 420 school districts, but after dividing our entire sample into two groups, the first group with a small class, we have 238 districts, and the other ones belong to the large group. So again, we're going to estimate the difference between those two groups in terms of the average score, and then we're going to test hypothesis that so our initial assumption is there shouldn't be any difference. That is going to be our hypothesis. Using this data, we're going to test this hypothesis. And then we're going to construct confidence interval about the difference in test score. So estimate of the difference in test score is so simple. Okay, so once you have this summary statistic for each group, then just take the difference between these two numbers. So then the difference turns out to be 7.4. Okay, looks like there's a difference. Then question is this really meaningful difference or just some difference, right? Is this large enough to consider? Large enough to develop new policy recommendation? Or maybe this is not large enough for school teachers, but maybe for parents, this difference, although it seems very small, because the standard deviation is close to 20, and the difference is less than half of the standard deviation. So we can say statistically, the difference doesn't seem to be large. However, although the difference is small, some parents can be very serious about this small difference. Okay, luckily my parents didn't care about my education much, but I see many parents are very serious about small, very little things. So I think, yeah, I think for some group of people, small difference can be very different, very, very important. Anyway, so just looking at this number itself, we cannot say whether this difference is significant, economically significant, or statistically significant. We cannot say something like that. As an initial point, one thing that we can do using our statistic background is that we can say whether this is going to be statistically significant. At this point, maybe it's not easy to say whether this is economically significant, but at least we can say statistical significance, because we have this formula for the T ratio. So T ratio for the difference looks like this. You should be familiar with this formula, but even if you are not familiar with this formula, don't worry. For your exam, I'm going to give you the formula, the list of formula for the exam. Okay, so you don't have to memorize this formula. So the T ratio is the ratio. It has numerator and the denominator. Numerator is our estimate, and the denominator looks like this. So standard deviation. Basically, this is a weighted sum of standard deviation, and the weight comes from the sample size. So we can calculate the standard error of this estimated difference in test score. So the numerator is our estimator, and the denominator is the standard error of the estimator. What is the standard error? That is, estimator itself is a random variable, so it has a distribution. and the distribution has a variance, and square root of variance is the standard deviation. But when we don't know the true distribution, we don't know the true standard deviation. We only have sample. Then using our sample, we can estimate the standard deviation. So estimated standard deviation is called standard error. So here, this standard error is the estimated standard deviation of these two difference. Actually, this name is more general. This applies to the difference of two y variables, but it applies more generally. More generally, sorry, why do I go back? More generally, whenever you have estimator, you want to know the standard deviation of the estimator. But you don't know the standard deviation of the estimator because you don't know the true distribution. But you have data. So using data, when you estimate the standard deviation of the estimator, that estimate is called the standard error. Okay? So using this summary statistic, and also using this formula, we can calculate this T ratio, and the T ratio is 4.05. In absolute value, this number is greater than 1.96. Then we can reject the null hypothesis at level of 5%. We are going to talk about more detail about this number 1.96 and level of the test and things like that. But at this point, I assume that you should be familiar about these numbers and terminologies like significance level, things like that. I'm going to pass this. But roughly speaking, in order to test, we have to calculate this tested statistic, in this case T ratio. And once we have T ratio, the tested statistic, then we're going to compare the T statistic against some critical value. And the critical value depends on the level of test, the significance level. And whenever the statistic is greater than the critical value, we reject the null hypothesis. Then what is our conclusion? We have strong evidence, statistical evidence, against our previous theory that says that there's no difference in terms of test score between these two groups. So looks like we have found some statistical evidence that one group has a higher test score than the other group. Another way to conduct hypothesis testing is to construct confidence interval. This is the formula for the confidence interval for this example. Example of difference in test score. The first term is the difference of the test score, which is our estimate, our estimator. So this is the interval, and interval is centered around our estimate, which means we're going to add something, we're going to subtract something. So we are going to add something and we're going to subtract something. Because the interval is centered around our estimate, we will add and subtract by the same number. This number depends on our critical value and our standard error. So using those numbers that we already seen, the critical value is 1.96. So it is going to be easy to compute the confidence interval. Confidence interval, this interval is between 3.8 and 11. This formula is pretty general. From the next week, we're going to learn OLS, linear regression technique. And through this semester, we're going to talk about more complicated estimation methodologies. However, whenever we need to construct confidence interval, the formula is going to be very similar to this. The first term is estimator, and the second term, so we're going to add and subtract something. The second term consists of our critical value and the standard error of our estimator. Okay, so the confidence interval is over here, and it doesn't include the value under the null hypothesis, which was 0. So we're going to reject the null hypothesis at the same level of the test. Right? Okay. Any question about this three procedure: estimation and hypothesis testing and the confidence interval? As you see over here, using confidence interval, we can do hypothesis testing. Construct the confidence interval, and we want to see whether the value under null hypothesis is in the confidence interval or not. If that is in the confidence interval, then we cannot reject the null hypothesis. But if it is outside the confidence interval, then we reject the null hypothesis. So basically, confidence interval is alternative way to conduct null hypothesis testing. There's these two things are closely related with each other. And in order to do this, we have to have estimator and standard error. And we need to have some idea about the distribution of our estimator, or the t ratio. Actually, this number comes from the fact that this t ratio is distributed as normal distribution with mean 0 and variance 1, which is a very important fact. We're going to review about that soon. Okay? Any questions so far? All right. So for next half of the course, what we are going to do is to review probability theory and statistics. Actually, I want to cover first 3 chapters of this book, because first 3 chapters are about introduction of econometrics and review of probability and review of statistics. These 3 chapters are very important for the other chapters in the book. Therefore, reviewing this kind of stuff, this material is very, very important. The prerequisite of this course is statistics and probability, or something equivalent to that. So I assume that everybody here has necessary background for a little bit more advanced materials. However, because today is the first lecture, I'm going to summarize these materials about the probability and statistics just briefly. I don't intend to teach something new to you guys, but I'm going to summarize what you already know. Okay, so basically, we're going to review something about the random variable and distribution, and we're going to come back to some simple example where we want to estimate some average population mean. And for that estimator, we're going to learn how to do hypothesis testing and how to construct confidence interval. Basically, this kind of things are a little bit repeating. It's kind of repetition of the example that we already seen. But we want to do this example with more abstract random variable, more abstract language. Okay? Okay, so random variable. What is a random variable? Actually, it is not easy to define random variable formally. But one thing that I want to keep in mind is random variable is not a fixed number. A random variable has lots of uncertainty. And this uncertainty is captured by distribution. When you have a random variable, you don't know what this number is exactly. But when you run experiment, that experiment will give you some results. And then this experimental results will determine the number of the random variable. Once the value of the random variable is determined, then you observe some number, like 5, 3, 20.5, something like that. As long as you have certain number, that is not a random variable anymore. That is realization of random variable. Okay? And like I said here, random variable is closely related to some experiment. Actually, random variable is a function. Function that converts outcomes of experiment to some numeric value. That is a random variable. Actually, the entity of the random variable is a function that explains outcomes of the experiment using the number that we can read. Okay? So, it is very important to understand the difference between random variable and outcomes of the random variable or realization of the random variable. You know, this is something that I didn't understand when I was a student. You know, I majored economics for my bachelor's degree, and I did master degree in economics, so I studied econometrics. But even after I wrote master thesis using some data, I still didn't have a good idea about the difference between random variable and the data that we can really observe. Only after I studied PhD level of statistics, I started figuring out the difference between random variable and the data. And after I understand that random variable is a function, not a number, I was able to learn more advanced stuff in statistics. And then finally I became an econometrician. But when I didn't have good concept of random variable, econometrics didn't make sense to me at all. Econometrics is the subject that I hated the most. I really hated econometrics. But after learning, after understanding the random variable correctly, I was able to learn more things. And then I met my supervisor, who was a really nice person. And that is why I became econometrician. Anyway, so how about having 10-minute break? Is that okay? If you like, I can continue on, and I can let you go like 10 minutes before. Okay, yeah. Let's have 10-minute break. We're going to start at 11 o'clock. Okay. Do you hear me? Okay. All right. You know, first of all, any question about last time? Any question about the course or the example that we covered? Anything? All right. So, yeah, actually, I forgot one thing. Maybe I have forgotten many other things, but I remember that I forgot one thing, at least. So, today is the first class, first meeting. So, I have so many students. And we all know that this lecture is going to be recorded. So there's a strong incentive for you guys not to come here, because you can listen to this lecture through online, and there's opportunities, which I really hate. The reason is because if even if I'm a student, maybe I don't want to come to the class, because I can listen to the lecture, and I know this. Maybe in the beginning of the semester, I can keep follow the lecture, first week and second week, and all of a sudden, there's something happened, and I became so busy, maybe because of other class or because of family, whatever, Then I might think that, oh yeah, the lecture recordings are there, I can listen to it anytime. So yeah, let's do that next week, tomorrow, the day after tomorrow. I can postpone it again and again, right? Actually, when I was a student, lectures were not recorded, so I don't have this experience. But for many other things, I have this kind of experience. I want to do this every day. I want to do, I want to do exercise every morning. So I do this for first few days. And then, because I did exercise for last 10 days, 2 weeks, every day in a row. So I deserve 1 day off. And that is the beginning of disaster. So I skip 1 day, and then why not 2 days, 3 days? I want to be in shape, but it's not easy to go to the gym every day. So what I want to say is, if you miss the class, I mean, you are allowed to miss the class, and you have all the freedom to do that. But I really encourage you to come to the class unless you have really good reason not to come. That will be very useful for you. Every week you will learn small amount of econometrics every week. So maybe it's easy to think that, oh yeah, I can study, I can teach this kind of thing to myself. I can teach myself this small amount. I can read the textbook. I can listen to the lecture. But when things are accumulated over a semester, it's not easy to handle within 2 days or 3 days. Okay? So I really encourage you to come to the lecture. And I really want to see you guys every week. I want you to come. I want you to come to the lecture every week. That is going to be eventually helpful for you guys. And also the research project, the homework assignment, is the same. I'm going to give you the problem set at least 2 weeks before the deadline of each homework. We have 2 homeworks, right? So you're going to have plenty of time to solve, to work on those problem sets. But not everyone, but some people just postpone it. Wait until one night before the deadline. And then email me. I don't know how to download the data set. How can I help that? No? Don't do that, please. It's my third year at UQ, and like I said before, I taught this course from 2 years ago. This is my third time to teach this course. Every year, some people are complaining that they cannot download the data set, they cannot open the software program just one night before the deadline. Sounds funny, but it's highly likely that some of you guys will repeat the same thing. Don't be that person, okay? When you have problem sets, try to solve those problems as soon as possible. Microphone, you cannot hear? Now, does everyone hear me? Hear my voice? Is it because of this one or because of that? I cannot I don't have control over that. I'm sorry about that. Yeah. Anyway, so any question? Okay, so my point is try to come to the class. And when you have a homework assignment, try to do that as soon as possible. These two are my points. Okay, so let me start with this experiment. Very interesting experiment that every statistics textbook does. The experiment is toss a coin, and this coin is fair. So probability of having head is 1/2, and probability of having tail is 1/2. Whenever outcome is tail, the random variable will give you 0. The number is 0. And whenever the outcome is head, the random variable will indicate that the outcome is head by saying that the number is 1. So like I said, this random variable is a function that maps from the experimental outcome to numeric value. In this case, possible numeric values are only 2, 0 and 1. Okay? We have 2 possible numeric values. In this case, especially, we can say that this random variable is a binary random variable. And when you toss a fair coin, then probability of 0 is 1/2, and probability of 1 is 1/2. And this probability function describes everything about this random variable. So actually, more generally, whenever you have some random variable, there must be underlying distribution that characterize the random variable. That is the rule. Whenever you have random variable, there must be distribution. So therefore, sometimes people are using random variable and distribution interchangeably, depending on the context. Okay? Now, but in many cases, we don't know the underlying distribution. Let's use a little bit of math to say that there is a distribution, and the distribution is distribution. This word is too long. So instead of the word distribution or the unknown underlying distribution, let's use this mathematical notation P. The reason why I have dot inside of this parenthesis is because you can use any symbol. You can use y, little y, or x. You can use any symbol instead of dot. So this is a common practice in mathematics, but don't be scared about this unfamiliar mathematical symbol. Thing is, we have underlying distribution. That is actually population. In this exercise, we have some population, and the population is characterized by this distribution, but the problem is we don't know the distribution, P here. If we know the distribution, then that's the same thing as we know the underlying population, and once we know the population, then there's no problem to solve. There's nothing to solve. We don't need to collect data. We don't need to construct confidence interval to learn something about the underlying world. Underlying world itself is population. We want to know about the population. How do we know of the population? Although we don't know the underlying population, we have sample that was generated from the population. we have many random variables that are coming from the same distribution. And because we say that they are identically distributed. So here we have double I and D. D is for distributed. And one of those I is identical. So these random variables are identically distributed. There's one more I because we want them to be independent. This sample, these random variables are independently and identically distributed, which means even if we know the value of y1, it doesn't have any information about the outcome of the y2. Even if we observe the realization of y1 and y2, we cannot have any additional information about the third random variable. So everything is independent with each other. Any one of them doesn't convey information about other random variables. That means these random variables are independent with each other. And because they are all coming from the same population or same distribution, they are identically distributed. Collecting those two, we can say they are IID from some distribution P. We can say identically independently distributed, or because this is too short, we can say just IID from some population distribution P. We don't know underlying P, but we observe a bunch of random variables. Whenever these random variables are IID, we say that we have random sample. And if you want to emphasize the sample size, we can say we have random sample of size n, little n. Usually we use little n to denote the sample size. But depending on the author, they could use uppercase n or m or some other letter. But you should figure it out from the context. But in this course, we're going to use little n for the sample size. If you look at this equation 1, mathematical expression 1, then what you have on the left-hand side, these are all random variables. So they are not numbers. They are collection of functions. Each one of them maps underlying experiment to some number, right? So we don't know what's the underlying experiments. We don't know what's the experimental outcome. But many cases, we observe numbers. We observe data. They are realization of the random sample. And in order to make distinction, when we are using uppercase letters, they are random variables. When we are using lowercase letters, they are realization. For this lecture, for the first lecture, for the review of statistics. But later on, we're going to use lowercase variable or uppercase variable without making distinction between random variable and the realization of the random variables. But from the context, it has to be clear. Okay, so this population is something that we don't know, but we observe the random variables over here. More accurately speaking, we observe the realization of the random variables. But let's say for now we observe the random variables, so collection of all the functions. And the econometricians, we want to know some important features of the underlying population distribution. So distribution is the same thing as population. Here in statistics, population has nothing to do with the population of Australia or population of America. That population is different from statistical, technical term population. Population is characterized by the distribution, and we want to know some features of the population. It may not be possible to know everything about the population, but we want to know some things, some important things about the population. So we want to estimate those important features. So that procedure is called estimation. And after estimating the important features, we still have lots of uncertainty because as long as we don't know the population exactly, what we are doing is we want to make a good guess about what's the population, what's the underlying population using the random sample. So what we estimated is not going to be exactly the same as the population, which means we still have lots of uncertainty. And we need to summarize the uncertainty in a scientific way. That is called inference. And two very famous examples of inference is hypothesis testing and confidence interval. Okay, so what are those important features of the population? One is expectation of the random variable. This expectation is often called population mean or just mean. But if you want to emphasize that this population mean, this expectation is the true population expectation, then you can say population mean. And using mathematical symbols, we are using these things to denote expectation. Expectation of y, the first one is very straightforward. And many statistical books are using the Greek letter mu for the expectation. And the underlying random variable is y, so we add subscript y. Or just simply, we can just use mu, depending on the context. What is population mean? Roughly speaking, that measures the central tendency of the distribution, or long-run average of y. So if you keep observing the sample, the random variable y over and over again, then when you take the average, then that is going to be close to the population mean. So that is what I mean by long-run average. And this population mean is one of the measure that is widely used for central tendency of the distribution. Another way to think of expectation is this. So here, imagine the situation of the problem of prediction. So random variable y has lots of uncertainty, but you want to make a prediction by choosing one number. Say you want to predict y by choosing some number a. And because you are going to choose a fixed number a, but there's a variability of the random variable y, you are going to make a mistake. It's inevitable to make a mistake. And the mistake is measured by the difference between the actual random variable and your choice A. And because this is sometimes, this can be negative and sometimes positive. So you want to have positive measure. That is, you square this difference. And you take the long-run average. And you want to minimize your mistake by choosing A, by solving this minimization problem. And the solution to this minimization problem turns out to be expectation of y. So more technically speaking, this function over here is called loss function. Statistician or econometrician measure their sadness associated with making mistake by this loss function. And when we have a loss function, we want to take an action to minimize the loss function. And this is the statistical problem. And expectation is the solution to minimize our loss in this case. Another very important feature of the underlying population is variance. Likewise, we can emphasize this variance is associated with the population by saying it is population variance. When we take the square root of the variance, then it becomes standard deviation or population standard deviation. Okay? So we have a mean expectation, that is a central tendency of the distribution, and the variance, that is a variation of the random variable. How diffuse? What's the amount of uncertainty around the random variable? That is measured by the variance. So once you know the location of the distribution, and once you know the size of the random variable, then you have pretty good idea about the underlying random variable or underlying population. Here we're going to think about statistical problem to measure, to estimate the underlying population mean. In this example, we are not going to talk about how to estimate the variance. We're going to talk about how to estimate the first feature, which is population mean. So again, we observe a random sample of size n. We have collection of random variables that are coming from the identical distribution, and they are all independent with each other. We want to estimate the population mean using sample mean. So here, this is the definition of the sample mean. And whenever we have equality sign, then that means the left-hand side is the same as the right-hand side. But when we put these two dots right before equality sign, we read it like left-hand side is defined as the right-hand side. So colon equality sign is different from just equality sign. So the y bar is defined as sum of the random sample divided by little n, the sample size. And here, this one is estimator for the population mean. If the sample size is not important in the context, then we can just say y bar. Or underlying population parameter is mu y. Then in order to emphasize that this thing, mu y, is the parameter that we want to estimate, often we put just a hat to say that this, mu is the thing that we want to estimate. Because yi, these are all the random variables. Function of random variable, y bar, is also random variable. I said every random variable is characterized by some distribution, right? Because y bar is a random variable, there must be a distribution that characterizes y bar. Okay? So now we want to figure out the distribution of the estimator using the fact that each y is distributed as some distribution, and each one of them has the same mean and the same variance. So these are the information that we have. But we don't know the value of mu and value of sigma square. We don't know exact value. We only know that each one of them, each y, has the same mean and same variance, and they are independent with each other. That is the information that we have. Okay, the reason why we want to have the distribution of our estimator is because we want to say whether our estimator is precise or accurate, something like that. We want to have some idea about how good our estimator is. So in order to do that, we need to have distribution of the estimator. Okay. Yeah, so once again, I want to emphasize that this mu and sigma square explain some part of the population, but econometrician, we don't know the exact number for those two things. These are unknown parameters, and we are interested in estimating population mean using the sample. Okay, I already explained about this. IID with the same mean and same variance, this is the only information that we have. I told you we are not going to prove anything when it comes to statistical results, but under our information, under our assumption, it is actually very easy to show that expectation of our estimator is equal to the parameter that we want to estimate. That is equal to the mean, population mean of each one of those random variable y, right? Because our estimator has the same expectation, the expectation of our estimator is exactly the same as the population that we want to know. We often say our estimator is unbiased. What is expectation? Expectation is central tendency of the distribution. By saying that estimator has an expectation that is the same as the population mean that we want to know, we are saying that the location of our estimator is centered around the unknown parameter, which is a really good property of of the estimator. Okay. So because this is expectation, all the properties of the expectation applies to this expectation as well. This is a central tendency, and the long-run average of this one, blah, blah, okay? So unbiasedness is a very good statistical property of the estimator. And also another thing is, turns out that the y bar is the solution to minimize this sample analog of the statistical loss function. So you remember that expectation is a solution to this loss function, and instead of this expectation, if you have average, instead of expectation, if you have average, then we can say that the sample average is the solution to this minimization problem. So a sample mean is minimizing our error to predict the next value of the random variable y. Unbiasedness is very important property as an estimator, but unbiasedness itself doesn't say much about the estimator. You want to have unbiased estimator, but unbiasedness itself is not really saying that your estimator is important, because so think about this situation. You observe a bunch of random variables, but for some reason you throw away many of these things, keeping just the first one, y1. And then you want to use this just y1 as your estimator. Even in that case, your estimator is unbiased. Why? Because when you take expectation of y1, then expectation is the same as the underlying population parameter, right? So just the first observation is the same as sample mean if you only care about unbiasedness. There's no difference because both of them are unbiased. However, we can say that sample mean has to be better estimator than just using only the first random variable. Why? Because we know that we know this second result. We can calculate the variance of the estimator. Turns out that the variance is equal to the underlying population variance divided by the sample size, right? Then if you have a large sample, then variance is going to be small for your estimator, which means the central tendency of the estimator is fixed at the underlying population parameter mu, and the variance measures the variability. When you increase the sample size, it goes like this. So if you have a large sample, then comfortably you can say that our estimator is close to the underlying population parameter that we want to estimate. But if we use only the first random variable as an estimator, then regardless of the sample size, the variance is going to be the same, right? So having a large sample doesn't matter if you're using only the first outcome to estimate the parameter. Only when you are using the entire sample, you can say that the variance is decreasing when you increase the sample, right? Therefore, your estimator is going to be very close to the underlying population parameter. That is concept of consistency of the estimator. If you increase sample size, your estimator is going to be very close to the population parameter. That property is called consistency. You want to have consistent estimator. You want to have unbiased estimator and also consistent estimator. And another concept is efficiency. We are comparing two estimators. One is y bar, and the other one is y1. When the sample size is 1, then both have the same variance. Y bar has sigma square divided by 1, which is the sigma square. Y1 also has the same variance, but as long as the sample size is larger than 1, variance of sample mean is smaller than variance of Y1. You have the same, you have two estimators. One has smaller variance than the other. Then this one, the one with the smaller variance, is said to be efficient, more efficient than the other. You have class of estimators, and one of them has the smallest variance. Then you say that that estimator is the efficient, most efficient, or just simply efficient. So efficiency is another statistical property that you want to have when you have estimator. Okay, sample variance can be measured by this, and turns out that this estimator is also consistent. When sample size increases, when you compute this, then this number is going to be close to the population variance. The reason why we are doing this is because we want to estimate the variance of the estimator. From this expression, remember this one, sigma squared divided by n. The standard deviation of our estimator y bar is just square root of our variance. Then it becomes sigma divided by square root of n. We don't know this population parameter, but we can consistently estimate this one using this, right? So here we have sample. This is something that we observe, and the y bar, something that we can compute. Therefore, we can compute this whole thing. We don't know the true value of sigma, but we can estimate sigma by using this. So estimated standard deviation of the estimator is called standard error. So this is the formula for standard error when the estimator is sample mean. Again, whenever you have some estimator, you want to measure the standard deviation of the estimator. So you estimate the standard deviation. Then estimated standard deviation is called the standard error. This is not only for the sample mean. Later, we're going to calculate OLS estimator. The concept is the same. The standard deviation of our OLS estimator is called the standard error of the OLS estimator. The reason why we are interested in standard error is because when we take this ratio, turns out that when sample size increases to infinity, it approaches to the standard normal distribution. This is a really powerful result because when sample size is small, we don't know the distribution of this ratio. But when sample size is large, then it converges to the standard normal distribution, and we know standard normal distribution very well. We know everything about this distribution. If you look at the back of the statistics book or econometrics book, then you have table of the probability. You know, we know everything about this, which means when you have this ratio, we can approximate this the distribution of this ratio by standard normal distribution. Just as a side note, this result is called something like this, asymptotic distribution. So here, this ratio have asymptotic distribution of standard normal distribution. And in order to derive this result, we have to use central limit theorem and Slutsky lemma. It is possible to formally derive this result, but that is too involved. that is beyond the scope of this course. So we are not going to do that. But we just take this result. Here, this D and this arrow, that is read as converges in distribution. So because of this result, equation 3, because of equation 3, when sample is large, we can say that this ratio is approximately distributed as a standard normal distribution. And then we use this standard normal distribution for hypothesis testing and confidence interval. We can use this standard normal distribution for statistical inference. Many people who learned statistics might think that, oh, maybe this is exactly distributed as t distribution when sample size is small, right? There's a difference. So the starting point is different. In the beginning, we look at the statistical environment where we have IID sample. Each of them has the same mean mu and same variance sigma square. So this is the only information. I emphasized this a couple of times. This is the only information about our sample. It has the same mean and same variance, but we don't know what kind of distribution is the underlying distribution. We don't know about the distribution. It can be Bernoulli distribution, it can be binomial distribution, it can be normal distribution if you're lucky, but it can be any distribution. But we know the population mean is mu and variance is sigma squared. This is the only thing that we know. If we have more information that underlying distribution is also normal distribution, then we can say that this ratio is exactly distributed as t distribution. Without having this information, without having this normality assumption, we cannot say that this ratio is normally this ratio is distributed as some t distribution. One good thing is, regardless of the underlying distribution, this ratio is approximately distributed as standard distribution, standard normal distribution. Therefore, this result is so powerful. Without knowing, even when we don't know anything about the underlying distribution, we can still use the standard normal distribution for our statistical inference. So this is really powerful. This approximation holds even when underlying distribution is normal distribution. Turns out that t distribution approaches to the standard normal distribution when sample size goes to infinity. Actually, it converges to the standard normal distribution very quickly. If the sample size is greater than 50, it's already become very similar to the standard normal distribution. So you can still use the standard normal distribution as long as you have fairly good sample size. In statistics course, you start from normality assumption and then derive t distribution, and then you learn that t distribution approaches to the normal distribution. But in econometrics course, especially this course, we are not going to do that. I just want to mention that under some additional condition, this one is t distribution, but that result is not necessary because economic data are not normally distributed. In other words, this assumption is not reasonable for our purpose. Essentially, no economic data are distributed as normally, so this assumption is really, really unreasonable. And for most economic data, especially these days, the sample size is pretty large. So this approximation is very good. So that's why we are going to use this approximation for statistical inference. Instead of starting from normality assumption, we are not going to assume normality. But later, when it is necessary, we're going to introduce normality assumption just for certain topic, and then we're going to throw it away again. So here we have some example. Let's say we have random variable. It takes value 1 with probability 0.78, and it takes value 0 with the other probability 0.22. So this is a binary random variable, but the probability is different from 1/2. This is different from the experiment of tossing a coin. It takes value 1 with larger probability, and it is 0 with smaller probability. So let's think about the case where sample size is 2. Then when we take the sample mean, first of all, this underlying distribution is not normal distribution, but we want to know the distribution, asymptotic distribution of the sample mean. So here, the first panel is the case where we have sample size of 2. Then, how many possible values for the sample mean do we have? We have only 3 possible numbers. One is 0. We observe 2 random variables. If both of them are 0, then sample mean is also 0. If both of them are 1, then the sample mean is also 1. If one is 0 and the other one is 1, then the sample mean is 0.5. So we have 3 possible values for the sample mean. And when we take this ratio, it converts to something like this. So here, this is the distribution, exact distribution of sample mean for this random variable when sample size is 2. When sample size is 5, then the number of possible values for the sample mean, this ratio will increase like this. When sample size is 25, it becomes like this. You know, it's already quite close to the normal distribution. This line is the standard normal distribution. When sample size is 100, now you can really use standard normal distribution to approximate the distribution of this ratio, right? This t ratio. So regardless of this underlying distribution, you can use the standard normal distribution for approximating this ratio. Here, this Bernoulli distribution is very, very different from the normal distribution, but still this result holds. Even when sample size is only 25, you can still use normal distribution. Okay, we are going to use the standard normal distribution for statistical inference. Therefore, we need to study a little bit about standard normal distribution. Suppose we have random variable following standard normal distribution, then one thing that we know about the standard normal distribution is this probability. In absolute value, the random variable is less than 1.96. This probability is 5%, which means the other event, the less than or equal to 1.96 is 95%. That means the event that the absolute value of the random variable is greater than 1.96 is only 5%, right? So this event happens with very large probability, and the other event happens with small probability. So another way to look at this situation is that this event, the random variable in absolute value is less than 1.96, is quite likely, and the event that this absolute value is greater than 1.96 is unlikely. Unlikely because this happens with probability only 5%. So your friends say that this is a random variable with a standard normal distribution, but you observe the realization of the random variable, and it turns out that the observation is greater than 1.96. Then you might suspect that what your friends said may not be wrong, may not be right. So think about this. For some reason, you believe that the random variable is a standard normal distribution, and after running some experiment, turns out that the realization is 0.238. right? Then that is this case. So in absolute value, this is less than 1.96. Then you will be comfortable. Our belief is right. This must be our belief is right. This belief is still true. But how about the other case? The realization is a large number, 4.2, say. And then you will say that unlikely event happens, even if this belief is right. This is really unlikely. If this belief is with uncertainty, then you might doubt about your initial belief. So basically, this is the idea of a hypothesis testing. So instead of Z, let's use this ratio. We know that this is approximately distributed as a standard normal distribution. But here, we can calculate this, and we can calculate the denominator, but we still don't know the true population parameter mu. Because we don't know the population parameter mu, we need to have hypothesis. So under the null hypothesis, we believe that mu is equal to some number that we know. Often it is 0. Depending on the problem, it can be some other number. But mu superscript 0 is the number that you know. So under the null hypothesis, you believe that this is true. If the null hypothesis is correct, then when you plug this hypothesized number in this t-ratio formula, then you know that this is approximately distributed as a standard normal distribution. And we're going to follow exactly the same logic. Whenever this happens, this is likely if the null is right. But this event is unlikely. If this is unlikely, then you might say that, maybe our null hypothesis is not correct. You can suspect the validity of the null hypothesis. So you want to reject the null hypothesis. This is the usual story. Whenever this ratio is greater than 1.96 in absolute value, you reject the null hypothesis. But as a scientist, this is not the story. This is not the story. Why do we choose 1.96? Right? Actually, this number is associated with the fact that as long as there's a standard normal distribution, this event happens with 5%, and this 5% is very important. Okay, so even if the null hypothesis is right, this event can happen, right? If this happens, then you're going to reject the null hypothesis, even if the null is right? Which means you are rejecting the correct null hypothesis. You are making a mistake, and that mistake is called type 1 error. What is the probability of type 1 error? In this case, that is 5%. So you fix type 1 error probability, and then you are making a decision. And if it happens, your ratio is greater than 1.96, therefore you reject the null hypothesis, then you don't want to say, I reject the null hypothesis because of this. What you want to say is, you want to admit the possibility of making a mistake as a scientist. So honestly, you have to say that in this decision making, I can make a mistake, and that error probability is 5%. That error probability is called level of the test, or size of the test, or significance level of the test. So what you want to say is, we are rejecting the null hypothesis at 5% of level. By saying this, by attaching this number, you are admitting the possibility that you are making an error regarding this decision making, and the error probability is 5%. So we couldn't finish this today's lecture. So next week we're gonna finish this lecture, and then we will start talking about regression analysis with one random variable. All right. Again, my consultation hour starts from 12:30 to 2:30. So if you have any issue, just drop by my office.
Today's 12:30. Okay.
Do you know how to log out, shut down, sign out? Sign out.
Thank you, sir. I just want to ask, like, how many groups of people how many people can be in a group?
The project is.